This lecture is on substitution versus elimination, Part B. Now we come to energy diagrams. These are depictions of the energy changes that occur as the reaction proceeds from reactant to product, and a demonstration visually of the different intermediate structures or transition states that exist during this reaction progression. Energy diagrams are really something that we teach organic chemistry students because physical chemists and physical organic chemists pretty much demand it. I would say that I've never used energy diagrams in 22 years as a practicing organic chemist, but you're going to see them on the American Chemical Society exam, in organic chemistry. You'll see them potentially on the MCAT or the PCAT. So it's really obligatory for me to show you energy diagrams. So we'll begin with the SN1 energy diagram. The reaction shown is the reaction of 2-chloro-2-methyl-propane in methanol to form 2-methoxy-2-methyl-propane and hydrochloric acid. In the energy diagram, we know that the first and rate determining step is dissociation of the carbon-chlorine bond. So what we do is we show this big hill, and at the top of that hill is the transition state where we show a dotted line between the carbon and the chlorine atom with partial charges, partial plus for the C, partial minus for the Cl, the transition state leading to the carbocation, which is at the valley between the first hill and the second hill. That valley is an intermediate. See, it's less stable than the starting material, but it's more stable than the transition state. So it has some transient stability. So there's our tertiary carbocation. Now we go up to another hill, which is a smaller hill, fast step, in which the methanol molecule is reacting with the carbocation. So we show a partial positive charge on the carbon and a dotted line as the bond is developing between the C and the O, and a partial positive charge on the O. Now we slide down that hill to an intermediate product, which is about as stable as the starting material, and this is the protonated product. Now another small hill, another fast step for the deprotonation step. So you show a partial positive charge on oxygen, partial positive charge on hydrogen, and a dotted line between the O and the H because that bond is being broken. Also a dotted line between the partially positive H and a partially negative Cl, as Cl minus is trying to strip away that proton. The final products in this case are lower in energy than the starting material, so our final compounds, the 2-methoxy-2-methylpropane and the HCl, are shown at the bottom in a valley, and that's the overall process. In our next energy diagram, we have E1 with weak base. So in our example reaction, again it's 2-chloro-2-methylpropane in methanol, but now I've thrown in a weak base, acetate anion. So our major product is the alkene plus chloride and acetic acid. In the energy diagram for this reaction, 2-chloro-2-methylpropane goes up a large hill in the first and rate determining step to form the transition state, showing the partially positive carbon dissociating from the partially negative chlorine, and that generates our carbocation intermediate, which is the valley. That carbocation intermediate then has a fast step, notice the small hill, and in this step the acetate anion deprotonates the beta hydrogen, and simultaneously electrons flow toward the carbocation. So you see a dotted line between the acetate anion and the proton, and a dotted line between H and C, since that bond is breaking, and a dotted line to the carbocation. And then, of course, our final products are the alkene plus acetic acid. In the energy diagram of an SN2 reaction, we'll use the example reaction of azide anion, N3-, reacting with the secondary alkyl halide, in this case a single enantiomer, to form the inverted product and bromide. So now in our energy diagram, azide has to come from the opposite direction of the carbon-bromine bond. This is inversion of configuration. You show a partial negative charge on N3, partial positive charge on the carbon, and a partial negative charge on the leaving group. There's only one energy barrier, only one transition state. There is no intermediate in this process. And at the bottom of the hill, you find your products. In the energy diagram for the E2 reaction, we'll use as our example the reaction of 2-chloro-2-methylpropane with hydroxide, which is a strong base, to form the alkene plus water and chloride anion. Our energy diagram, and again, just like SN2, only has one hill, because there's only one transition state, there's no intermediate. And in that transition state, hydroxide has a partial negative charge as it's pulling off the proton, which is partially positive. That's the beta proton. The alpha carbon is partially positive. Notice there's a partial double bond forming, and there's a partial bond between that alpha carbon and the leaving group chloride, which is partially negative. This is a concerted reaction. Everything happens simultaneously. The proton's being removed at the same time as the double bond is forming, at the same time that the chloride is being expelled. And again, our products, the alkene, water, and chloride, are shown at the bottom of the hill. Practice problem 4. Draw the energy diagram for the mechanism of the following reaction. So your job is to identify what that mechanism is first. Is it SN1, E1, SN2, or E2? And then to use one of the 4 templates that I've already shown you to create your energy diagram. At this point, you want to pause the video in order for you to work on the practice problem. Answers to practice problem 4. Well, you have a tertiary alkyl bromide reacting with water. That's an SN1 reaction. The water is a protic polar solvent, and the tertiary alkyl bromide can only undergo substitution via forming a carbocation. There is no other weak base, so there's no E1, and since it's tertiary, you can't do SN2. So we start off with the 2-bromo-2-methylpropane on the bottom left, going up the highest energy barrier, the rate determining step, to the transition state where the carbon-bromine bond is breaking. That's the dotted line between the partially positive carbon and the partially negative bromine. That forms our intermediate carbocation in that valley. The carbocation then reacts in a fast step, that's the small hill, to generate the transition state between water and the carbocation. So we have a partially positive carbon with a dotted line to a partially positive oxygen. That falls downhill to our first significant product, which is the protonated alcohol. Now another tiny hill as bromide removes proton from the protonated alcohol. So you have partially positive oxygen, the dotted line to the proton that's being removed, that's partially positive, and a dotted line between that H and the Br where you form the HBr bond. Br is partially negative. That falls down the hill to form our final products, the alcohol plus HBr. SN2 versus E2. SN2 is a competitor for E2. So since these two reaction mechanisms are in competition, we have to understand them well enough to be able to determine which one is faster under certain conditions. E2 reactions require strong bases, such as hydroxide, OH minus, an sp3 hybridized carbon attached to O minus, or stronger bases like Nr2 minus, C minus, where carbon is negatively charged and is either an alkane like C single bond C minus, or CH3 minus, an alkenyl anion such as C double bond C minus, or alkynyl anion such as C triple bond C minus. The mechanism is concerted. Okay, everything happens at once, and the beta hydrogen in the alpha Cl, that is the bond between the alpha carbon and the leaving group, must be anti-paraplanar for flexible molecules. Remember, that means that that bond between the beta hydrogen CH bond and the alpha Cl bond are in the same plane, but they're 180 degrees across from each other. That's anti-paraplanar. It must be syn-paraplanar for rigid molecules. Same plane, but now the angle between the bonds is 0 degrees. So if you look at the examples, in the anti-paraplanar case for a flexible molecule, you see the beta CH bond and the alpha Cl bond are anti-paraplanar. The strong base deprotonates, and simultaneously the electrons flow toward the alpha carbon, displacing the leaving group. Just as a reminder, when you use arrow notation, the arrow that's forming the double bond goes from that CH bond, that is beta, and goes to the middle of the bond between the two carbons, because the electrons are being shared between the two carbons. And then you show the displacement of the leaving group. The electrons flow completely to the L, so the arrow tip should go toward the L. That forms your alkene plus the protonated base and the leaving group. Under rigid conditions, such as in this alkene situation, where there is a beta hydrogen and an alpha leaving group, you can be either syn or anti-paraplanar. We're showing the syn-paraplanar example. You have the strong base again, removing that proton. Again, concerted mechanism. The electrons flow toward the leaving group, but the arrow is shown in the middle because the electrons are going to be shared. The leaving group is displaced. You get a triple bond plus the protonated base and the leaving group. In another rigid case, which cannot be anti-paraplanar because that wouldn't actually exist in this bridged ring system, only the syn scenario is paraplanar. So the base is able to remove the beta hydrogen, the electrons flow between the two carbons, and then displace the leaving group to give you a double bond. Now that we've taken a look at the conditions that make E2 work, let's figure out when E2 is faster than SN2. If a beta hydrogen is present, and you need that, otherwise you can't get a pi bond for E2, the rate of E2 will be greater than that of SN2 under the following minimum conditions. That is, the minimum size and strength of base. It can be stronger, but this is the bare minimum. For a tertiary center where the carbon has a leaving group, hydroxide is that minimum sized base. There's no SN2 anyway because it's tertiary, and E1 is much slower because you're using a strong base, even in a protopolar solvent. For a secondary carbon with a leaving group, you need now hot hydroxide. You can also use sp3 hybridized carbon attached to O minus, or if you really want to make sure this is just E2, you can use this bulky base called DBU. DBU is an E2 only base, making mostly the more substituted, most stable alkene if possible, so it follows Saytzeff's rule. And the structure of DBU is shown. A primary carbon with a leaving group will perform E2 faster than SN2 when you have a really bulky strong base. And the prototypical example is tert butoxide, O minus connected to a carbon with 3 methyls, or O minus TBU. It's tert butoxide. It's a very bulky base that prefers to make, in this case, the less substituted alkene if possible. That's known as Hofmann elimination. It's because it's so bulky that it would be a slower reaction if it tried to grab a proton from a more substituted position to make the more substituted alkene. Thus, given the possibility of 2 different alkenes, tert butoxide will prefer to form the less substituted alkene. If beta hydrogen is not present, your carbon bounded to the leaving group is methyl, primary or secondary, and you have a nucleophile, even if it's a strong base, and your solvent is aprotic polar, the only reaction that you're going to get is SN2. Remember, without the beta hydrogen, you can't get elimination. So even if you have a strong base, you're still going to get SN2. Practice problem 5. Predict the major product or products of each of the following reactions. If no reaction occurs, write NR and explain. Now, this practice problem involves only SN2 versus E2. So there are no SN1 or E1 reactions present. At this point, you want to pause the video in order for you to work on the practice problem. Answers to practice problem 5. In part A, DBU acts as an E2 only base. Therefore, the secondary alkyl chloride will be eliminated to form an alkene. We want to form the Zaitsev product, that is, where the carbon-carbon double bond is most substituted. So as you can see, we remove the beta hydrogen that's at the position of greatest substitution and the alpha CCl bond, thus giving us the double bond with most substitution. In part B, potassium tertbutoxide is a very bulky base, and it prefers to form the less substituted elimination product, or Hofmann elimination product. So instead of finding the hydrogen on the carbon that's the most substituted, we now look at the terminal carbon, which is the least substituted, and use that beta hydrogen, forming a terminal carbon-carbon double bond. In part C, we have a reaction with methoxide as the base. Again, this is an E2 reaction. It's a secondary carbon with a leaving group with a base that is strong, specifically sp3 hybridized carbon next to O-, and that means that E2 is preferable. In this situation, it's hard to tell where the beta hydrogen is, so we draw a Newman projection and rotate it so that the tosylate leaving group is anti-paraplanar to the beta hydrogen. Then show methoxide removing the beta hydrogen and displacing the leaving group. That gives us our final product. There's only one product because there's only one appropriately positioned beta hydrogen and alpha leaving group. In part D, you have the same substrate, the tosylate leaving group, but now we've changed to the nucleophile NaSCH3, which is a weak base, sulfur instead of oxygen, and now we have an SN2 reaction being faster than an E2. Displacement of the tosylate will occur with inversion of configuration. Since tosylate is coming towards you, the sulfur will come in from the back and will be positioned away from you in the product. In part E, we have tertbutoxide again, and we have a primary alkyl bromide. Tertbutoxide will perform an E2 reaction even with a primary carbon to a leaving group, and so we get a terminal carbon-carbon double bond. In part F, we have a tertiary benzylic system. You might think, oh, okay, we may get SN1 or E1 here, but solvent is DMSO, which is aprotic polar. That means we only have two choices. We can have SN2 is impossible, right? So we can have E2 or no reaction. E2 is possible if we have a strong base. But we're using sodium cyanide. That's only a weak base. So there's no reaction. SN1 or E1 is impossible because of the nature of the solvent. SN2 is impossible because it's tertiary. And E2 doesn't work because of the weak base. So this is an overall no reaction case. In part G, we have the same compound with the tertiary alkyl chloride that's benzylic. Again, it's an aprotic polar solvent, but now sodium hydroxide is a strong base capable of performing an E2 reaction. There's a choice of E2 reactions that could occur, and the one that we pick is the one that's going to generate the most substituted alkene following Zaitsev's rule. And in part H, we have a secondary carbon with a leaving group of bromine, but there is no beta hydrogen, so E2 is impossible. So even though we have the strong base, sodium methoxide, NaOCH3, the only reaction that can occur here is SN2. So the bromide is replaced by methoxide to give us the final product. RS and EZ nomenclature. For single enantiomers of compounds, the RS designations, also called CIP notations for the discoverers, Kahn, Ingold, and Prelog, are given in parentheses in front of the compound name. As you can see in the example, we have two stereogenic centers. As an alcohol, we want to number from left to right. So the base name is 3-bromo-butan-2-ol, and the stereogenic centers are 2R and 3S. So the full name is 2R, 3S, 3-bromo-butan-2-ol. With C double bond C containing 4 different groups, we can't talk about cis or trans anymore. That doesn't work. Instead, we use the atomic priority system, just like we learned from the RS system or the CIP notations. On one carbon in the double bond, we designate the number 1 atomic priority to one of the groups, and on the other carbon in the double bond, we do the same thing. We designate a number 1 group on that side. If the two number 1 atomic priority groups are on the same side of the double bond, then we call that Z. If the two number 1 atomic priority groups are across from each other, we call that E. The numbered position for E or Z is optional if there's only one E or Z designation. If there are multiple E or Zs, you have to use the numbers. You also want to make sure the numbers for the E and Z are in numerical order when they're put in front of the name inside the parentheses. A mixture of RS and EZ is placed in front of the name, again, in numerical order in parentheses. So as you see in the examples, the one on the left, the chlorine is number 1 on the left side of the carbon-carbon double bond, and the bromine is number 1 on the right side of the carbon-carbon double bond. Thus, the number 1 groups are on the same side of the double bond. If you think of the top side as being the same side, and thus this is Z or 2Z, 2-bromo, 3-chloropent, 2-ene. The diastereomer, flipping the chlorine to the bottom, now has the number 1 atomic priority groups diagonally across from each other. So this is now E or 2E, 2-bromo, 3-chloropent, 2-ene. Practice problem 6. Name the following compound. This compound will have a mixture of E and Z and R and S designations. Answer to practice problem 6. In this compound, we have to number from the upper right to the bottom left in order to give the position of the carbon with the OH the lowest possible number. That's a stereogenic center as well, so we'll have to use an RS designation. There are also 2 carbon-carbon double bonds with 4 different groups on them, so we need to use the E or Z designations. The stereogenic center at position 2 is R, and the E or Z designations are as shown. For position 3, that's E. For position 5, that's Z. Now, you can tell for position 3 because the carbon on the right side has a substituent of C to O, and that would be number 1 and versus H. And the carbon on the left side of the double bond has a carbon, a methyl group, versus a carbon, a chlorine. So that means that those two groups, the C to O and the C to Cl, are diagonally across, and thus E. For position 5, that is Z, because we have The highest atomic priority group is chlorine on the bottom right, and the carbon from the methyl on the bottom left. Thus, they're on the same side with Z. So the full name for this compound is 2R, 3E, 5Z, note the numerical order, 5-chloro, 4-methyl, hepta, 3,5-diene, 2-ol. Practice problem 7. Draw 1E, 4R, 5E, 1-chloro, 5-ethyl, 2-methyl, nona, 1,5-diene, 4-ol, which is quite a mouthful. What you want to do is try to draw the structure from the end of the name to the front of the name. That will make it a lot easier. So focus on the nona 1,5-diene 4-ol portion first. Get that right. Then put on the substituents of 1-chloro, 5-ethyl, 2-methyl. Then deal with the EZ and RS designations at the end. Answer to practice problem 7. Alright, now just as I described, you want to put in the ol and the enes first, along with the carbon chain length, which is 9. So we have a 1,5-diene, so that means we have to put the carbon-carbon double bonds at positions 1 and 5. We have a 4-ol, so the OH group comes at position 4. Now we can deal with the substituents of 1-chloro, 2-methyl, 5-ethyl. And finally, we want to deal with the stereochemistry. We have the 1E stereochemistry and the 5E stereochemistry established. And at position 4, we see that that is 4R.